This video is going to look at the mechanism behind acid-base reactions in organic chemistry. And these are reactions that you're familiar with from introductory chemistry, but we're going to think about them in terms of arrows and nucleophiles and electrophiles. This video will just talk in general about acids and bases, and then later we'll talk about how to quantify how good an acid or a base is with pH, pKa values, things like that. And then we'll talk about some specific acids and bases that you see in organic chemistry. Okay, so let's think first about some strong acids and strong bases. Typical ones that you see are things like hydrochloric acid as a strong acid. Sometimes you see sulfuric acid, and bases typically is some hydroxide salt, like sodium hydroxide or potassium hydroxide. So we can imagine, as an acid reacts with a base, what forms? Well, water in this case plus a salt, and the salt will be sodium chloride. This should be familiar from intro chem, but let's think a little bit about drawing the mechanism behind this reaction using our arrows. Now, for strong acids, the definition of a strong acid is for every molecule of that acid, you generate a molecule of H+, or if it's an aqueous solution, H3O+. So we can really think of strong acids as being like salts also. They dissociate when dissolved. And so for hydrochloric acid, we might imagine that that is an H+, plus a Cl-, and that's a fair way about thinking about that molecule. That's only true for strong acids. Weak acids, only a very small fraction of a population of molecules will dissociate. Okay, sodium hydroxide is a salt, and so it will dissociate to form sodium plus and OH minus. Okay, now how are these molecules going to interact, and what's the mechanism of this reaction? Well, if we think about how to use arrows, then we have to identify some nucleophiles and electrophiles. And with the acid and base reaction, I'm going to focus on the H+ and the OH-. These are acids and bases. And so we're going to obviously react these two things together, and we're going to connect them together. The question is, how are we going to draw the arrow? Well, we have a base here in our hydroxide. It's not just a Bronsted base that is going to accept the proton, but it also is a Lewis base that's going to donate electrons to the hydrogen. This lone pair is going to form a new bond between the oxygen and the hydrogen, and that generates our H2O. Okay. That's really the only part of the mechanism that is necessary to form the water. Sodium chloride, again, is going to be a salt in an aqueous solution, is going to remain as a sodium and a chloride. You can almost think of these as spectator ions, right, that don't contribute to the reaction. Now, students often want the arrow to go from the hydrochloric acid to the base. They're used to the Bronsted definition of what an acid is, where this hydrogen is being donated by the acid. Now, that's true. However, remember, when we think of arrows, we're thinking about electron movement. And so it is incorrect to show an arrow from the hydrogen to the hydroxide, ending at the hydroxide. We need to show the arrow going from the source of electrons, which is the base, Lewis base, to the electrophile that's accepting those electrons, acting as a Lewis acid. So if we identify the acids and bases in here, HCl is acting as a Bronsted acid because it is donating a proton. It is also acting as a Lewis acid because it is accepting electrons. The hydroxide is acting as a Bronsted base because it is accepting this proton to form water. It's also acting as a Lewis base because it's donating electrons. Okay. Now let's look at an interaction between a weak acid and a weak base. And here's an example. Ethanol is a weak acid. Can also act as a weak base. And if we react it with ammonia, we can describe through a mechanism how a weak acid and a weak base can interact. Here's a lone pair from our base that is going to be donated to form a new bond with this proton. That would generate too many bonds on that hydrogen, and so that bond will break, and those electrons will form a new lone pair on the oxygen of ethanol. So if we think of the products of that reaction, what do these arrows describe? Our ethanol has been converted to an ethoxide anion. Our ammonia turned to ammonium. And that's the acid-base reaction. Okay. Here's our weak acid. It's a Bronsted acid because it's donating a proton to ammonia. It's acting as a Lewis acid because it's accepting electrons from our ammonium. And this is acting as a Lewis base because it's accepting a proton. It's also acting as a Lewis, it's a Bronsted base because it's accepting that proton. Okay, a Lewis base, let me say that again. Lewis base because it's donating electrons. Bronsted base because it's accepting that proton. Okay. Here's our acid. Here's its conjugate base. Here's our base and its conjugate acid.